Good evening, ladies and gentlemen. Good evening. Struggling. There we go. Good evening, ladies and gentlemen. Please rise as we welcome the procession inside the venue. Thank you so much. Thank you. You may be seated.
Good evening, colleagues and friends. Welcome to you, Stellenbosch University, Science Faculty. We apologize for the weather, but looking at the attendance, we obviously know and we can see that tonight's speaker is a very popular person. So thank you for being here. On behalf of Professor Ma and the Science Faculty, I wish to welcome you. Special welcome to our Rector, Professor de Villiers, our DVC, Professor Moyo, our COO, Professor Duplessis, our other two DVCs, Professor Ramjankanot and Professor Klopper. Distinguished colleagues, welcome. We know that you will enjoy tonight. So, as part of this welcome, we asked Yin-Zhe for a list of dignitaries that we have to welcome. I think he virtually sent the name of every person in the hall tonight. So, please, if we do not mention you specifically, it's not because you're not special to us, not because you're not special to Yin-Zhe, but we simply do not have the time. So, a special welcome to Dr. Rob Adam from the SKA Observatory, ex-director of Sarao, who was also awarded an honorary doctorate by Stellenbosch University last year. Mr. Takalani Nemongani, Chief Director of Astronomy, Department of Science and Technology. Professor Marcus Butcher, Professor South African Research Chair at Northwest University. Professor Suber Razak, Professor and Director of Center for Astroparticle Physics, University of Johannesburg. Professor Leon Koopmans, Director of the Kaptein Astronomy Institute, Groningen University. Professor Matthew Collins, Distinguished Professor at the Australian National University. Professor Emma Trolley, Professor of the the Swiss Federal Institute of Technology, Lausanne, Mr. Yi, Science Council of the Consulate General of China from Cape Town, Professor Chen, Head of Galaxy and Cosmology Division, National Astronomical Observatory of China, Professor Han, Chinese Academy of Sciences, and Dr. Zhu, Director of Beijing Planetarium. And then a special welcome to Professor Ma's family and friends, and a special welcome to his mother. Welcome. Colleagues, it was my duty only to do the welcome, but give me extra 2 minutes, please. I thought of, when was the first time I met Professor Ma? And I believe it was in 2016, when he did a presentation as part of the Nobel Laureate series. And I hosted him as the acting Deputy Vice Chancellor of Research and Innovation. And after his presentation, I had some of his colleagues and some of my colleagues, and some colleagues, international colleagues, coming to me to say, you know, this man will probably be a Nobel laureate himself one day. So I think we're very honored to have him here today to listen to those stories. Those who know Yin-Zhe knows that he has a lot of energy. And he takes that energy and that passion not only to his research, but to his private life as well. And I hope, as part of his presentation tonight, he's going to speak about his camel riding adventures in Egypt, and even does that type of things with passion. So colleagues, please enjoy tonight, and we look forward to Professor Ma's presentation. And I would like to invite Professor Moyo now to the podium, please.
Good evening, everyone. I think you were supposed to clap for the dean when he finished, so can we do that? Thank you so much. And welcome to this amazing lecture today. We are in for an interesting time, so a special welcome, of course, to the colleagues and friends of Professor Yin-Zhe Ma. So you've all been welcomed by name, so I'll not do that, but in particular, of course, his mother, Mrs. Yu-Ching Lu, who's with us today. Ni hao, ni hao, thank you very much. Professor Yin-Zhe Ma, of course, Professor Yin-Zhe Ma is finalizing currently the establishment of the chair in computational astronomy at Stellenbosch University. He obtained his physics bachelor's degree from Nanjing University, and then a master's degree from the Institute of Theoretical Physics at the Chinese Academy of Sciences, and a PhD in astronomy from the University of Cambridge. Having served as a National Fellow of the Canadian Institute for Theoretical Physics and Astrophysics at the University of British Columbia, and as a Research Fellow at the University of Manchester, he joined the University of KwaZulu-Natal in 2015 and was promoted to full professor in 2021. He was appointed to his current position at Stellenbosch University in 2023. So currently, Professor Ma, Yin-Zhe, is a fellow of the Academy of Science South Africa. His research is in the field of theoretical and computational astrophysics, and this field, of course, deepens our understanding of the fundamental laws of the universe and uncovers the nature of dark energy and dark matter. Professor Ma has been leading South Africa's participation in several international astronomy collaborations, and we are very privileged today, of course, to have the Department of Science and Innovation present, and of course, they have supported us significantly in this area, both for students and the research that we do. Of course, in this work, the research includes some of these international networks include the Square Kilometer Array, SKA, which you know about, the Meerkat Telescope, the Planck Science Team, the Hydrogen Epoch Reionization Array, HERA, the Cosmic Microwave Background CMB experiment, and the Legacy Survey of Space and Time at the Vera C. Rubin Observatory. His publications include over 130 papers, which have earned him more than 29,000 citations. He was elected to the Academy of Science, of course, of South Africa in 2022 and to the Royal Society of South Africa's Council in 2021 and 2023. When he received the NRF B rating, his argument was that it was not good enough, so he's aiming for an A. We had a lot of discussions around this, and we believe that indeed, he'll be the next Nobel Prize winner. He's aiming for that as well. He's very ambitious, but also very hardworking. He argued with the NRF that they must check the research. I remember that it wasn't at the same level as a B rating. So we look forward to his lecture. Professor Yin-Zhe is very passionate about learning and teaching, so he exercises the same excellence as he does in his research. Very passionate about training students. And I believe here, are there any of the students from the group in this room? Can you raise your hand? Yeah? Postdocs, students. So it's a very big team that he has built in a very short time, and you can see by his presence. So today we also had a great privilege of meeting our counterpart. I mentioned earlier that we are establishing a chair in computational astronomy. So we've been visited by Professor Leon, who's also visiting from Groningen University, from the Kaptein Astronomical Institute at the university. This institute has over 350 students interested in astronomy. So as part of the chair which Professor Yin-Zhe is planning to establish at the university, we also aspire to bring the same number and scale of students to the physics department and the science faculty at the university, as well as have spin-off companies just like the counterparts have at University of Groningen. So congratulating for this and also for always being sensitive to the gender gap. One of the aspirations is also to encourage women in science, and it's one of his goals as well. So we look forward to the lecture as Professor Yin-Zhe presents. Please clap and welcome him to the floor. Thank you.
Down a bit. We all try to find the meaning of life. Something serves as a purpose, something that is unimaginary, yet inspires us. I find my meaning of life when I was a second-year undergraduate student at Nanjing University while listening to an interesting talk by Professor Lu Tan. He presented me this picture, which shows the entire evolution of the universe. Do you have a laser pointer here? I was told you have a laser pointer supplied to here. Yeah. Which shows the entire evolution of the universe. It started from a hot Big Bang, then expanded until it's cold enough to neutralize atoms. Oh, okay. If I touch the screen, then it will show something?
It shows on.
Okay.
It's only on.
All right, good. And then it's entering into dark ages until 500 million years, the first star and galaxy formed and reionized the universe. Then the dark energy kicked in and drive the universe accelerate expansion. I was fascinated because it's not obvious at all that we humans on a tiny little planet in this enormous, vast amount of space could possibly answer questions about the universe as a whole. But modern technology has allowed us to measure the old light from these early emitters early on and use the laws of physics to answer these questions. This is a pretty audacious undertaking. So you won't be surprised to hearing that there are still mysteries to crack. The whole story starts from Einstein, who published the theory of relativity in 1916. He wrote down these famous Einstein field equations, which shows the interplay between the matter and space-time. In the short term, the matter on the right-hand side tells us how space would curve, and vice versa, the space would tell how matter would move. Initially, he thought the universe was static, but he got a shocking news from his friend Edwin Hubble in 1929 that the universe is actually expanding. The Hubble measured the receding velocity of the distant galaxies as a function of distance and found that the further away the galaxy is, the faster it's moving away from us. So the entire universe is not the miniature of today's universe. We're not smaller at early time, but it might be expanding and evolved. The wrong picture of the Big Bang, therefore, is this explosive scenario, like a bump. I always be asked such questions. But the correct picture is this evolution scenario where if we track down to the beginning, then everything was squashed into the very hot and very dense plasma. So the first evidence of this hot Big Bang coming from this big nuclear synthesis. George Gamow said in the early 1950s that if the universe was sufficiently hot, then it should synthesize significant helium. Helium, you learn chemistry here, and also you can see the helium here on the wall. But in order to form the helium, you have to form enough deuterium, the isotope of hydrogen, then the two deuterium has to combine to form a helium particle, either through this way or from this way. So the binding energy of deuterium would be 10 to the 10 Kelvin, so much larger than the recombination temperature. And this is sufficient to distinguish from the stellar evolution because the center of stars is only around 10 to the 7 Kelvin, which will produce no more than 2% of the helium in the universe. So the modern technique coming from this Lime alpha forest, a distant quasar, which is shown here, can emit a continuous spectrum over a range of UV wavelengths. And while the radiation is penetrating through the cold intergalactic medium, it will produce a lot of absorption trough along the way, which can be used to determine the column density of the deuterium. So this is one of the interesting simulations done by one of my colleagues, Andrew Pungsen. So by measuring this absorption trough, you can actually deduce the amount of deuterium in this metal-poor damp Lime alpha forest system. And this is what people actually found. So the top panel is the helium abundance, the medium panel is the deuterium, and lower is lithium. This Cook et al., he measured the deuterium abundance through the damp Lime alpha forest system, and he got this y-axis point. And this line itself is actually the Big Bang nuclear synthesis calculations. By inserting with the baryon density measure from the cosmic microwave background radiation, which I will mention in a moment, then you get a consistent result of the deuterium abundance measured from this Lime alpha forest system. So it means the theory of BBN really works. So now we can have a better understanding of the periodic table of elements. I'm showing here and also showing here on the wall. And this is the chemist one. So if I see the same table from astronomer's point of view, I see something like this, which show the detailed astrophysical processes that produce these heavy elements. Of course, the hydrogen and helium are mostly from the Big Bang fusion, where the other element coming from different post-astrophysical processes. If I ask a lady who wear a gold ring, where does the gold come from? The physical answer, gold is here, the physical answer would be coming from the merging of the two neutron stars. So if I see the same table, using another view, this is an astronomer, but if I use cosmology's perspective, I see something like this. Here I make the area proportional to the cosmic abundance. So hydrogen is about 74%, helium is 24%, and the all other element adding together is less than 2%. The amazing thing is that this table does not change by more than 1% since the universe was 3 minutes. So 3 minutes all the way up to now, which is 13.7 billion years, this table does not change by more than 1%. Isn't that impressive? That's the reason I love this subject. So after the hot Big Bang, the universe keeps on expanding until 380,000 years, where the photon lost interaction and decoupled from the hot plasma. We call this recombination period, which is really just a neutralization of the period of the atoms. And the physics of this is actually very simple. At the very early universe, everything mixed as a hot plasma, and then perturbation just propagate at a sound speed. At a time of 300. Because of the size of the universe. And baryon propagate to a distance of 150 megaparsec from the center of the perturbations and form a gravitational potential well, and then which attracts dark matter falling into it. So you will see this characteristic correlation of 150 megaparsec for matters in the universe. And this is another interesting animation showing how this sound wave would propagate Of course, this is just one simple perturbation, but universe is full of random fluctuations. So you not only have one perturbation, but you see many random perturbations that superpose together some pretty blurred pictures. So this is just like a quiet water pond. If you drop a stone, then it will make ripples. Then you see a regular pattern of hot rain, cold rain, hot rain, and cold rain, and so on. However, universe has many random fluctuations, so it's just like dropping many stones, you see superpositions of the hot spot and cold spot on the sky. And that is exactly what you see in the cosmic microwave background radiation, the map we measure from WMAP and Planck. So this indeed, pattern of the cold and hot spot is indeed what you see the fluctuations of the universe at 380,000 years after Big Bang. So now the question is, if this is true, can I reconstruct the ripple? Can I reconstruct a single hot spot and cold ring from the map? The answer is yes, and actually it's quite simple. If you take all of the hot spot and you cut a circle of a few degrees from it and stack all of them together, and then you see something like this. Around each of the hot spot, there's a cold ring. The average, of course, is just like when you make the ripple on the water. So average is still the flat, but it will make little perturbations. And then around each of the cold spot, there's a hot ring. Same for WMAP and same for Planck. So without doing any complicated data analysis, without any complicated Fourier analysis and so on, you can download the map, which is publicly available, write a code for 2 hours, then you can see the most important effect in the early universe. I sometimes give this task to my students who want to do computer astronomy just to warm up the skills. Also on this map, you see fluctuations on different scales. And for example, the universe on here doesn't look much different from the universe over there. So there's a correlation among the scales on the sky. So from 1980s, people try to measure the correlation of the fluctuations at different angular scale on the sky. And this is the journey of the CMB experiment, which I'm fortunate to catch up the latest train of this journey. As you can see, back to the 1980s, the error of data was so large, these are the data by then, the error is so large that it could not tell anything about the underlying model, which is shown here, the black solid line. And we can see now, as the technique improved in the last 30 years, the noise will be bring down, and the equipment will be better calibrated. Telescope beam is improved, so the smaller angular scale will be covered. And then also the data will also measure the large angular scales if the sky coverage becomes bigger. So let me fast forward the last 30 years to see what happened. So this is 1980s, 1990s, early 1990s, 1990, mid 1990, 1990s, late 1990, and the year of 2000, 2002, 2004, 2006. By then, when I read undergraduate student in China, the inflation with lambda, with cosmological constant, Einstein lambda, is confirmed. The cosmic string has been ruled out because it's unable to produce a coherent fluctuation on the sky. 2006, the same year I went to Cambridge to study the PhD. And Cambridge is a great place. I came to study at the Institute of Astronomy with Professor George F. Darcieux and Anthony Challenger. At leisure time, I went to punt on the Cam River. I'm a pretty good punter, generally. And this is a picture with Malcolm Longhair, the supervisor of South Africa's Bernie van der Hoef, who showed me, interestingly, the desk used by James Clerk Maxwell. The desk of Maxwell. What an interesting thing to see. The important opportunity for me is the launch of the Planck satellite by the European Space Agency. I started to write down the code for Planck data, eventually got a PhD on it in 2011. And this is the graduation day in Trinity College, Cambridge, where Lord Martin Rees, the Astronomer Royal, came to congratulate me. So then this is the power spectrum just before the Planck released. And this is Planck 2013, 14, all the way up to 18. As you can see here, the data become exquisite at this stage. The error bar on this higher L become so small that the thickness of the curve is invisible. The theory of lambda CDM, the Einstein's cosmological constant, plus cold dark matter, can magically go through all points. And I must say, this error on small l over here is not due to the experimental error, but due to the cosmic variance. Because the universe is the biggest thing we can see, and we have a limited number of modes on the sky on these very large angular scales. And there's no way to beat down these error bars. And you can see in the last 30 years, which is really a revolution, that the measurement of the microwave background radiation coming from this very poor measurement all the way to this exquisite measurement. And this is one of the most impressive progresses in astrophysics. And the detailed amplitude of the shape of this power spectrum is related to many important physics. The low L power spectrum is related to the large-scale CMB anisotropy, and this of L is due to the inflation, and location of the first peak is determined by dark energy because it's determined the projected angle of the Kusi horizon on the sky. And these peaks due to the baryon-Coulson oscillations, and damping wind is determined by the reionization and also the optical depths. And small angular power spectrum is due to the Sanyaev-Zerdovich effect, the cluster effect. So my recent years research revolve around this power spectrum, as you can see the thing I've been doing. And if you allow the free parameter of the universe to vary and use this data, this exquisite measurement to constrain these parameters, then you see something like this. And these are the most important parameters relevant to the global property of the universe. So NS is the tilt of the scalar perturbation, which is close to unity, 0.97 something, means that the fluctuation is almost the same amplitude across different wavelengths. H0 is a Hubble constant. 67 means the universe expands at a speed of 67 kilometers per second per megaparsec scale. Here is a fractional dark energy density. Here is a fractional matter density. So these two adding together is almost 1. If you can calculate by eye, so these two adding together almost 1. And that means the spatial curvature is almost 0. This means the 4-dimensional space-time is still curved, but 3-dimensional space embedded into it can be flat. And the age of the universe, which is 13.7 billion years over here, is a big but finite number. I believe for thousands of years, philosophers may have wondered what is the longest time of physical reality. Of course, they had no clue. And now we can answer such interesting philosophical questions using modern technology and even give you error on such answer. Isn't that remarkable? And very importantly is this interesting pie chart, which shows dark energy contribute to the 69% of the universe budget, dark matter 26%, and the atoms, everything included, you, me, the table, everything is 5%. So dark energy only is kind of an energy which has a repulsive force driving the universe accelerated expansion. And dark matter have gravity, but we don't know its particle nature, which I will cover in a moment. And the atoms, only 10%, for this 5% of the chart, actually only 10% of the atoms has made into stars and galaxies, whereas a lot of them are actually diffused. They are the missing baryon in the universe. And this is part of research in the last couple of years. So I try to fill the gap of the missing baryon, which is to find the evidence to detect those missing baryons, and also try to find the evidence to find the particle nature of dark matter. So let me talk about the missing baryon first, which is my recent research. And this is the early simulation by Sen and Ostriker. You can see that interesting simulations. You can see majority of the gas at low redshift is in the temperature range 10 to the 5 to 10 to the 7 Kelvin, something called warm-hot intergalactic medium. This is the major reservoir of baryons at low redshift. So these illustrative simulations have shown you that many of these baryons are actually reside in filaments or in void, which are different morphologies of the larger structure of the universe. So what I'm interested in is to use the CMB, the cosmic microwave background radiation that has emitted from the 380,000 years after the Big Bang, as a backlight to probe these foreground structures, the cosmic web, which is a secondary anisotropy of the CMB. And this is the effect of how electrons around the gas clusters, and they can inverse content scatter the CMB photon, travel a long way from the last scanning surface And by this, the electron would distort the CMB parabolic spectrum, produce a characteristic Y distortion, which directly proportional to the pressure profile of the hot gas. So a few years ago, I cross-correlated CMB, a map, Compton Y map, with gravitational lensing, and produced, this is the gravitational lensing from CFHT, the Canada France Hawaii telescope, and I feed this data is also here, with a theoretical model that doing the lensing, calculate the lensing on Compton Y cross-correlation. I find that if the gas is extended to the 5 times of the real radius, then the data can fit the theory can fit the data very well and on all angular scales. But if the gas is only localized in the center of the gaseous clusters, then you produce a red curve, which is showing here, that is below the data on all angular scales, which is a deficit signal. So it means the hot gas much more extended further beyond the center of the halos around the gaseous clusters. We also want to see some direct evidence of the hot gas in filament. So we stacked 260,000 pairs of the large luminous red galaxies on the Compton Y map, uniform the size, and then try to subtract the disk from these two sides, and therefore find the residual signals in the filaments. And then we can quantify this residual signal, which is over here, and do an amount of random sample on the sky, and we find this residual signal, which is about this value, 1.3 times 10 to the minus 8, which indicating that the hot gas temperature in the universe is about 10 to the 6 Kelvin. So we find this evidence observationally. Previously, people were just doing numerical simulation and generate that from the computer. And this is from real observations. In a recent work I did with my students, we stacked the Sloan Digital Sky Survey cosmic void on the Compton Y map. So the cosmic void is this empty region in the sky, which has much lower density than the mean density of the universe. And the void is empty region on the sky, so we stack them, we see a deficit signal in the middle, which is showing over here. This is the data, and we can fit a theory line to the data, and we find the hot gas is actually inside the void, satisfy this equation, so that's a density contrast. You see a minus sign because the void density contrast itself is negative, so minus delta V is positive quantity. So we can find the temperature of the hot gas is about 10 to the 5 Kelvin. So those are some details, but what I'm trying to say is we want to complete this missing baryon search in the next few years. So this is a general picture of what's going on. So the diagram shows dark matter density on the horizontal axis, the baryon density on the vertical axis, and the dashed line are the empirical boundary lines between halo, filament, and void. So of course, halo is occupying larger density, filament is somewhere in the middle, void is a low density in the universe. So if the baryon completely trace the underlying dark matter, then all points should be falling onto this line. And the slope is the cosmic mean value, the baryon density divided by total matter density. But you can see, look like something here deviate, the data is from here and enrich the data over here. So basically by feedback, by the AGN feedback or other feedback mechanism, the baryon density is being modulated, so halo have a little deficit and voids and filament have a little bit enrichment. So to search the missing baryon completely, we have to do the checkup of this equation observationally. So the baryon in the void plus baryon in the filament plus baryon in the halos plus those neutral ones in the cluster has to be 100%. It has to be there. So we know it's there. It just we need to, observationally determine the factor of this and to confirm that picture. Okay, so much for the visible matter. Now I'm moving to the invisible matter, which is dark matter. Unfortunately, it's a huge scale to search. From the matter as low mass as 10 to the minus 22 electrovolt is energy density because mass equals energy by Einstein, so I'm just using that convention, to all the way to the mass as heavy as 10 to the 27 electrovolts, we call primordial black holes. And we have no clue whatsoever that dark matter on that axis is. If you know it, tell me, but I don't know. We know it exists, it must be there, but we don't know what particle whatsoever it is. What's going on? So basically what I'm saying is this axion-like particle, AOP, would be occupying at a very low mass end. As you know, you heard about the wave and particle duality. So if a particle that is really massless, then the wavelengths would be long. So the wavelengths of the axion-like particle will be the size of the galaxy. So you have a macroscopic effect of the quantum particle. And to this axion, to the WIMP, the weakly interactive massive particle, all the way up to the primordial black holes, which really collapse into a black hole as a perturbation enter into the horizon after the inflation. So for example, the physics department is involving in an experiment called PAUL, P-A-U-L, using the Hugo tunnel in Western Cape, which is an underground laboratory to search for the WIMP dark matter over here. So the technique which I'm developing is to search this axion dark matter using radio telescope, using Meerkat array and SKA. The axion and photon are actually the same thing when they travel inside the magnetic field. So if you have axion here, then it can be converted into a photon in the presence of the strong magnetic field. The probability is this Ga gamma factor. In astronomy, the stronger magnetic field is, of course, the outskirt of the neutron star. So the best place to look for it is outskirt of neutron star. And we basically gear the telescope to some of the neutron stars and then get some data from it. And the strong magnetic field of neutron star can just convert the axion into radio wave and therefore being detected by the Meerkat telescope, for instance. Here, this is one page I intended to confuse you about theoretical result we have derived. What we measure is the average flux density in each frequency channel, which is related to the distance to the neutron star and the width of the channel, and very importantly, this power per solid angle of the emitting power of the neutron star. And this power per solid angle, of course, related to several physical parameters of neutron star, the radius, the mass of axion, the magnetic field, and also several of the geometric factors. Okay? And then, so eventually this would be a theory line we are computed, and we're getting data from Meerkat, and we analyze it. And here we go. And this is one of the work I did with my student. We use Meerkat telescope to search for these axions, and this is spectrum we get. So the upper panel is the spectrum. This is rho mean square. This is a signal to noise ratio. Unfortunately, we don't see any signal above 5 sigma. Otherwise, I would be extremely excited. There are rare peak above 5 sigma, so we can say we exclude some of the parameter space of axions. The blue region over here is the excluded region of axion parameter space. But there are still, as you can see, it fills over here. There's still empty region to fill. So I think the future Meerkat extended array, Meerkat Plus, and SKA can help to fill some of this gap and maybe find axions somewhere lurking there. So my current and future research program include this period. I'm saying these two, one is missing baryon, one is dark matter. But future program include this very important period of the cosmic dawn and reionization, which happened 500 million years after the Big Bang, which is the major goal of the SKA, the Square Kilometer Array, and also the James Webb Space Telescope. And that is the last unexploited territory in the universe. So I would say this is really the last thing we don't know, because before 380,000 years, the universe was in hot plasma, and we can use the thermal equilibrium physics to describe it. And in fact, we can calculate the deuterium abundance and helium abundance and verify with data, which I have just shown to you. And later time, the galaxy formed, and the Sloan Zero Sky Survey and many galaxy survey has mapped out a quarter of the sky, all to almost redshift 1. So the future DAISY survey and Vera-C Rubin Observatory can improve it. So the intermediate stage is this is really a mysterious part which we haven't yet systematically studied. And so I just want to advertise that we just have enough tool to study this period by using the radio telescope. So it's a golden time to probe this area of research. So let's see what it is. The universe was neutral after recombination. Then 1 billion years after the Big Bang, the gravitational potential attracted a lot of baryons and gas to form the first stars and galaxies, which emit ultraviolet radiations. And this UV radiation can reionize the neutral hydrogen, so from a little bubble, and that gradually grow to reionize the remaining neutral hydrogen and make universe ionize again. And in this video, you can see the little seeds of ionization will gradually grow. The first star and first galaxy bubble will gradually grow bigger and bigger, eventually eat out all of the remaining neutral hydrogen region neutral intergalactic medium. So it's a really fancy video, look like magic. You're just staring at it. Soon will become completely transparent. Here we go. So now it's all, neutral hydrogen is all gone. It's all reionized universe. And searching for this ionization source is indeed the motivation for the Hubble Space Telescope and also James Webb. A decade ago, this Hubble Space Telescope used a few hundred hours to survey a dark sky area, just a few arcminute across. You need 100 of such to cover the full moon. With no known galaxy and star whatsoever in that region before. And they return this picture. You see all of these little smudges. And each of these is an entire galaxy. The reason previous survey didn't see it because they are so faint, so far away. But as long as you have enough time, enough sensitivity, then you can see them. So they are very far away, so that's why this picture is called Hubble Ultra Deep Field. There's a lot of discussion here in the current conference in the IAU. And for James Webb Space Telescope, it has 5 to 6 more collecting areas, 100 times, it can measure 100 times fainter object. Hopefully it will reach redshift 20, which is really very, very early on, and which is just 1 billion years after Big Bang. Really want to find those first stars and galaxies. But for radio astronomy, here we adopt a different strategy. Instead of searching for individual source, we search for the continuous neutral hydrogen medium that prevail in the early universe. The neutral hydrogen has electron and proton, and their spin can be in parallel or in anti-parallel. And the transition between the two, these called hyperfine splitting states, would radiate a photon with wavelengths equals 21 centimeter. So the observed wavelength in the rest would be the rest frame wavelength, 21 centimeter times 1 plus z factor. That z is the redshift factor. So if you observe a photon emitted from reionization early on, for instance, redshift 9, 9 plus 1 is 10. 10 plus times 21 centimeter is 210 centimeter, 2.1 meter. 2.5 meter is this long. So that's a meter wave. So you need a radio telescope to measure it. In fact, that's what we're doing. The hydrogen epoch reionization ray, HERA. And that is really like a brother of the Meerkat ray, because in the Karoo Desert, you can see each other. They are just 2 kilometers away in the desert. No, the bush is low, so you can see them in between. So that is the HERA itself is a 350 dishes in Karoo Desert of South Africa, and each of them is 14-meter dish, and the frequency of detector is about 50 to 250 megahertz. So therefore, the redshift coverage would be 4 to 27. Exactly cover the transition of the universe between neutral to ionized. If I return to this, 4 to 7 redshift would be this one, this 4 would be here, and 27 would be here. It exactly covers this area which universe transit from neutral to ionized. So here is one of the Google Map, Google Earth location. So you can see that directly where it's located in our Karoo Desert, the Northern Cape Province, one of the most radio quiet location on the planet. And you can see it's a giant hexagon array and in the desert with a few outriggers. So this is the current limit so far. These are different upper limits achieved from different radio telescope in the world, including LOFAR in Europe and Murchison Wide-Field Array in Australia, and also GMRT in India. And our HERA team published this milestone upper limit one year ago at redshift 8 and 10. So it's still 100 times higher than the underlying theory curve, the fiducial model, but it's one of the tightest constraints so far. So in the next few years, we hope to push down this upper limit and to make it touch the underlying curve and to achieve the first detection of the data. So compared to the CMB, so this is what happened in the CMB in the 1980s. 30 years ago, it also seems hopeless. The data error bar is so big compared to the underlying theory, but now the data is so exquisite that you can check, you can really verify the underlying model and therefore deduce a parameter from it. So I just want to say, for the one we're doing, 21 centimeter we're doing, is also 100 times larger than the unknown theory. So we are going through this revolution path right now. With so many unknown questions, so many darks, the nature of dark matter, dark energy, missing baryon, and so on, the future is actually quite bright, because data will gradually reveal the physical nature. The future CMB survey would include this bicep array, bicep cake array, and South Pole telescope in Antarctica, and also Atacama Cosmological telescope in Chile, and Simon Observatory and Ali experiment in the Tibet province of China, and also the library experiment by Japanese and American astronomers. Future galaxy survey is the James Webb Space Telescope by NASA, the Euclid telescope by European Space Agency, the Vera C. Rubin Observatory, and also DESI telescope, and also this called Nancy Roman telescope, also by the US. Another important window is radio astronomy. So Meerkat telescope in South Africa will certainly play a role, and it will merge into the SKA in a few years' time. The FAST telescope in the Guizhou province of China, the single biggest telescope in the world. The Hira telescope in South Africa, and this is the RISH telescope that I heard that our engineering friends is actually building, and this is the Murchison Wide-Field Array in Australia. So all of these telescopes receive signals from the pulse-like cone or within the pulse-like cone. This is a pretty busy plot, maybe confuse you again, but I'm showing you that the horizontal axis is the three-dimensional space, and vertical axis is the word line in the co-moving coordinate. So we can observe the pulse-like cone all the way to the last scanning surface by using the electromagnetic spectrum. Of course, if we can observe gravitational wave or neutrinos, or have a neutrino telescope, then it can change. I'm showing you a movie now that what we might see if we fly out of the space, fly out of the solar system, all the way back to the beginning, hypothetically, what we can see. Okay, here we go. Here we are basically in the Earth system, Earth-Sun system, and then as we fly away, we see Mars, the Jupiter, the Saturn, with a nice ring, and gradually we find ourselves in the middle of the interstellar medium, which is in one of the spiral arms of Milky Way. And further flying out, we see actually the external galaxy like the Andromeda that is 700 kiloparsec away from us, which is actually crashing into our own galaxy in 6 billion years' time. And as we flying further away, we see distant galaxies and stars. And as we fly further and further, we see things become younger and younger because it takes time for this light to reach us, and then dark ages, and all the way to the beginning, which is hot, dense plasma. And that is the thermal equilibrium initially we see from the microwave background radiation. So this video compressed the 13.7 billion years into just a few seconds. So science has extended our knowledge and the universe much beyond the physical reach. And there are still much we do not understand, such as first moment, the nature of dark matter and dark energy. So there will be new discovery in the future. So I think if I summarize the hierarchical structure of the universe, everything you can see, I think I can summarize in this plot. I call Ouroboros. The image picks up rather nicely the interconnectedness of the microworld on the left and cosmos on the right, the inner space of atoms and the outer space of the universe. As a link, and there are links between small and large, left and right. Our everyday world, life on mountains, is determined by molecule and chemistry. And higher up on the picture, the star, like our sun, is actually powered by nuclear fusion. So there's a link between the star and the nuclear physics. And higher up on the picture, there's another link, because the galaxy form is due to the gravitational pull of the subnuclear particles that are made of the dark matter. So there's a link between the subnuclear particles on the left and the galaxy on the right. And the left-hand side is the domain of the quantum, and the right-hand side is the domain of the cosmos. So now general relativity, Einstein theory, and quantum theory are the two great pillars of the 20th century physics, but they haven't yet meshed into together to form a single unified theory. In most content, this doesn't impede us because the domain of relevance don't overlap. Astronomers can ignore the quantum fuzziness when they are thinking the orbit of the planet, At the same time, you never heard about chemists worry about gravitational interaction between atoms or molecules, because that's 40 order magnitude smaller than the electron force between. However, at the beginning of the universe, everything has been squashed all together. So the quantum fluctuation actually shaking the entire universe. So to confront the overwhelming mystery of what happened at that Big Bang, you need a unified theory of the quantum world and micro world, symbolized gastronomically on the diagram here. And we really need to understand the very large and very small and how they link together. I should mention that apart from the very large and very small, there's a third frontier, the very complex. And we ourselves are the most complex thing we know about the universe. We are the midway between the atom and stars. We are large enough compared to the atoms to develop layer upon layer of the intricate structures like the organs and so on, but not so large to be crashed down by the gravity on our own planet. And we are, in a rather precise sense, midway between the atom and stars. The geometric mean of the mass of the sun and mass of proton is about 50 kilograms. I can see it's within a factor of 2 of the mass of each one here. So it takes as many human body to make up the sun as the number of atoms inside each of us. So astronomy isn't just peering the stars through a telescope, it's also science to connecting the fundamental physics on micro world with astronomical observation on the grand cosmos, and to provide insights into the relationship between human being with the entire universe. In the last moments, I want to just answer a question of why Stellenbosch, why I come to this institution. Of course, it's a nice place to be, but there's a deeper reason. I can see Stellenbosch's great expertise of research, which can all be connected into astronomy. The physics department is pretty strong in theoretical physics and nuclear physics, and data school and CS department is pretty strong in data analysis, and engineering does a lot of radio antenna design, as we heard previously, and NESEX, which is doing theoretical and computational science, and so on. And of course, CS is a wonderful place for organizing conference, communication, and so on. Around this whole area, seeing astronomy is a missing link between them, between these different partners, and constituent in an important link among these disciplines. And what link I mean? I mean this link. Let me specialize in the way which astronomy can play a role in knowledge discovery. In fact, all of these different disciplines of university can be summarized into one pipeline: telescope, data, science. Telescope, I mean engineer, design, and build telescope, commission the instrument, and maintain the equipment. By data, I mean produce the first-tier calibration results, such as gain, bandpass, and so on, and flagging, RFI flagging, converting to the continuum or spectral images, and also that is make it ready for science. Finally, science, astrophysicists and astronomers can manipulate the data, calculate the observables, compute the theoretical predictions, and then draw physical conclusion of the universe. And this is the whole process from instrument to data, eventually to conceptual advances. And we have to push this whole thing to the end, because the conceptual advances, the change of notion in society, is the ultimate knowledge to pursue. Crick and Watson discovered the DNA double strand. Nobody still remember what actually fraction technique they use, or the data they collected from the helical molecules. But everyone knows DNA double helix, because that's the conceptual advances to achieve. So this is a unique equation we can build here: telescope, data, science. And we have all expertise here in this university, which is very rare in South Africa. So even though astronomy in Stellenbosch started only recently, we can rise up in niche areas in a unique way and to be distinctive. So this made me find the second meaning of my life, to construct a successful astronomy center in this very unique institution, to complete this entire pipeline of astronomy discovery, to inspire more young people to look at the sky and wonder its mystery. I hope this lecture has inspired some of the young mind in the audience to join me to unravel the mystery of the universe. Thank you so much.
Thank you very much. Wow. So I'm Wim de Villiers, I'm the Rector and Vice Chancellor, and my duty this afternoon is to deliver the Rectorate response and the handover of the certificate for this inaugural professorial lecture. Congratulations. Then it's a pleasure to deliver the Rectorate response, and that's a little bit more difficult. Following on from such a tour de force, such a spectacular exposition, and such a beautiful lecture, and also a presentation. I must say the visual presentation was absolutely outstanding. So, an inaugural professorial lecture is a very important event in the life of an academic. It's a signal event in the life of an academic, because that is one finally professes. You profess the tenets of your discipline. And it speaks to, and as we also discovered this afternoon, is that becoming a professor is not a sprint. It is a marathon. It's a slog. It takes a long time. It takes a lot of hard work. Therefore, it's such a pleasure to also welcome Yin-Zhe's mother here, and also his friends and some of his colleagues to help attest to this wonderful, to this event. So I must say, how can one resist attending a lecture with the title "Unravelling the Mysteries of the Universe"? And I said my name is Wim de Villiers, so it's W-I-M. It's not WIMP, it's not W-I-M-P, but I now know that I could also be a weakly interactive massive particle. I think one thing that I do want to take home is, if you want to unravel the mysteries of the universe, you need energy. And wow, we certainly witnessed that in spades. So you can understand why we were so excited at Yin-Zhe joining us in 2023 for the formation also of the Chair of Computational Astronomy. So when I first entered this lecture room this afternoon, I actually must tell you I had some trepidation and anxiety, because it took me back to my first year medicine and chemistry and organic chemistry. It wasn't as nice as this. It was much older, before it was beautifully refurbished, but it was full to the rafters there, both in this lecture and in the one below, with hundreds of us. And the lecturer would stand here and say, I just want to tell you that look to your left and look to your right. You won't see those folks at the end of the year. And that was pretty intimidating. So I'm pleased to be here again and to experience this. So I didn't know that Yin-Zhe, in all of this, what I also learned this afternoon is Yin-Zhe is actually a romantic at heart. I mean, he talks about romance, and he talks about the mysteries of the universe. He talks about gold rings and love. And it's the merging of neutron stars. And that's what gold is about. I didn't know that. So that's fantastic. Yin-Zhe, you're a softie. So I was, however, disappointed to hear that he went to Cambridge. Having gone to Oxford myself, it's merely the other place. And they punt from the wrong side. They do it from the back. We do it from the front. So, but it is really wonderful. So, the mysteries of the universe. So, I am a gastroenterologist by training, so I'm in a small way trying to unravel the mysteries of the gut. We have Professor Stan Duplessis here, the COO. He's trying to unravel the mysteries of our budget model. But I must say, Yin-Zhe, you are certainly busying yourself with much bigger questions. And also, if we think about, this is really an interdisciplinary, multidisciplinary effort, with theologians and philosophers also very much interested in unraveling the mysteries of the universe. A little while ago, I read a book written by Jim Holt. It's certainly focused on the lay public. Jim Holt, Why Does the World Exist? An existential detective story. It's addressing some of these questions also with a philosophical intent. And I thought I had a reasonable handle on it. Yin-Zhe, you certainly took it to a next level. But I recently noticed that there was a sort of a comment on this book, and it said, no, it's actually all a cosmic conspiracy. I think this all could be a Truman Show. Maybe we just exist for the entertainment of some higher species, and we will never find that out until we die. So I just want to say this was a truly enjoyable lecture, truly enjoyable. Enjoyed being on this journey with you, Yin-Zhe. I love your equation, and we look forward to solving that equation for you as we go forward. Thank you so much.
Thank you, Mr. De Villiers. My name is Sean Leingaard. I'm from the physics department. And I think maybe just before I say my vote of thanks to various people here, perhaps we should just thank Yin-Zhe again for this inspiring lecture. So colleagues and friends, it's my privilege to say a few words of thanks on behalf of the faculty and also our department at physics. I'd like to start off with the Rectorate for allowing this opportunity for us to gather here in this very small space of the universe. Professor De Villiers, Professor Muriel, Professor Duplessis, Professor Ramjuganot, Professor Klopper, and I would also like to thank our Dean, our very brand new Dean, Professor Bertram Fielding, who's recently joined us, for allowing us to have this opportunity to celebrate this milestone which was reached by Yin-Zhe this evening, which we're celebrating. I think Yin-Zhe spelled it out very nicely that there's actually space for all of us in exploring the mysteries of the universe. And I'm glad to see representation from other faculties as well, the Dean of Engineering, Professor Van Niekerk, also in the audience. So we would like to explore those opportunities, not to only unravel new knowledge about what the universe has to share, but to also join forces and create opportunities for our students. Then, of course, a very important part of science is our human interaction. I recently got reminded by a colleague at Professor Jansen at Education that, in fact, natural science is a social activity. That's why we are here. We are all here to collaborate, to work together, to share our amazing facilities and tools which allows us to pierce into the universe. And that is very important because this very moment we're sharing this wonderful opportunity which our colleague Professor Ma has given us. And along with us here at Stellenbosch University, we have many people who have traveled across the world. I'd like to maybe also share a word of thanks to Yin-Zhe's mom for being here and many of the colleagues who traveled afar from China, the Netherlands, other parts of the world. Some of you are also, in fact, attending this presentation online, sharing this moment with us. I'd like to thank you all for that. But we shouldn't forget about the people who have been working in the background for us to enjoy what has been presented to us in the past hour, as well as the opportunity for us to also engage in a more social environment. And I'd specifically like to thank Suzette Els. She's around here somewhere. from the Dean's Office, Science Faculty, Amir Brown and a team from the Marketing Division, Justin Alberts at the back, who's ensuring that everything is running smoothly in terms of the media, and all of you for being here. Those of you who are here in person, who's taken on this, the weather outside, the cold, wet weather, I'd like to thank you for being here, making this moment a warm-hearted moment which we would like to share with our colleague Yin-Zhe. And then I want to be a bit naughty as well, because I think Yin-Zhe presented an amazing talk. For me, he's our Big Bang moment, right? Bundle of energy. We've heard about amazing things which are still unexplored. And in fact, looking across this audience, I'm seeing a lot of young people. We're representing the sciences, physics, astronomy, astrophysics. And I think for our young people, there are amazing opportunities for you to explore, to, in fact, find opportunities, whether it is in the field which I'm in, nuclear physics, particle physics, the smaller universe, to the grander scale of things, and in between, studying the science or the physics of life. And I'd like to extend this invitation to you to come and join us here at Stellenbosch. Be part of this family, this community, that we all can grow together and actually learn from each other. So there's an opportunity, I think, for us to also engage and enjoy each other's company after this event. And I'd like to invite you to also share, if you like, refreshments, which I think will be served in the foyer. So from the faculty and the science department side, I would like to thank all of you for being here. Thank you very much. So last step, sorry, I almost forgot about this. There are procedures to follow, excuse me. So I would like to ask all of you to rise while we ask the academic procession to follow Yin-Zhe in exiting this venue. Thank you.